Okay, so we'll go ahead and announce the winners here. Okay, so the answer to our trivia question here is how many peaks above 14,000? Good to know as a pilot, if you're flying at 14,000 feet, is 77. So the way we get that, there's 58 in Colorado, 17 in California, and 2 in Washington, in the contiguous United States. Obviously, Alaska has quite a few more, but for those flying down here, that answers some dusty roads. You are the winner of the weather book.
All right.
There you go. Thanks to Mr. Rich, we have our second prize, which everybody is eligible for. Davey?
I'm named after a baseball player.
Oh, okay.
There you go. Thank you so much.
I was just telling him my dad's drills are up there.
Okay, I got just a couple quick things. First of all, I just got a note from Taylor Albrecht, so apologize for Don.
Can't hear you.
No way.
Okay.
Same guy. Yeah. Yeah.
I'm sorry.
Taylor has got another Centennial Tower tour set up, and he forgot to make a broad announcement on that. So if you're interested in that, it is for January 9th at 11 o'clock. He said the last one went very, very well. They got to go out on the catwalk outside the cabin and everything else. So if you're interested in that, see me, and we'll get you set up on that. What's the first signs and symptoms of hypoxia? One of the first potential signs. Possibly.
Impaired vision.
Euphoria. I've heard that over this. I've got hypoxia. I feel great. What could possibly go wrong? Drowsiness. Who all here has a high altitude endorsement in all books? How many would like to have or need to have a high altitude endorsement in all books? Have I got a deal for you? Taylor has engaged with a company called Air Fax Training. This is the company that goes around the country doing hypoxia awareness training. And they have it set up so that you can actually experience hypoxia, so you know what your signs and symptoms are, whether it's hypoxia, euphoria, headache, nausea, tiredness, etc., because everybody reacts differently to that. What this is ground training, and then also a decompression without going into a decompression chamber. In other words, they put a mask on you and then deprive you of oxygen, so you see what actually happens to you when you get into that situation. This is scheduled for the 17th of January. We have a limited number of slots open for this. The cost is $199. Normally they charge $750 for a one-off type of thing. So you can come here, come to IA, go through this training, and it authorizes you to have a high altitude endorsement in your logbook as well, without having to go up and run a 421 and do a high dive and all the other stuff that's involved with that. So if you're interested in that, see me after the seminar and we'll get you signed up for it. Okay? Any questions on anything? Okay. I think it's going to go all day long, two different total sessions. Okay, so we can work whatever you see. Thank you. The date is January 17th. Okay. And again, the price is $199 as opposed to $750. This is what they charge one off on that. Okay? Thanks, guys.
All right. By the way, I forgot to put out a couple of handouts that I put out on the back table. So during the next break, if you want to pick those up. One is aviation weather resources links that a lot of you have been here before and seen, but for those who don't have it or want to update, that is back there. Okay, so this one's kind of an interesting topic. I like to do it just because it's such a topic of conversation in so many circles. I want to stay as far away from the political side of this as I can. I want to stick to the scientific side. But obviously, sometimes politics and ideology comes into play when people talk about this topic. So we can certainly have a discussion. I'm very open to talking about this topic. What I want to talk about is really how is weather and climate related, and what are some of the drivers between weather and climate. So weather, is what we experience on a regular daily basis. It's greatly influenced by the climate of the planet at that time or the local area at that time. Climate is our long-term average of weather for a specific region of the planet. In the US, we tend to use a 30-year period. The National Weather Service, every 10-year period, every decade ending, they update their climate for all of the stations in their area. So right now, we're using the climate period from 1980 to 2010 is the climate period. When all you hear about here, temperatures above average, below average, that's what we're comparing it to, that 30-year period. Extremes, temperature records, are used for the entire length of the record history of Denver. That goes back to 1850-something. But when we talk about our averages, we talk about this 30-year climate period. Okay? So it changes every 10 years. Our Earth, in its 4.5 billion year history, has gone through some pretty dramatic climatic changes during that period, according to records that we've gathered through various means, through ice core samples from Greenland and Antarctica, from sea soil samples that go down. So scientists have collected this information, this data, and tried to extrapolate what the climate would have been at certain periods in history. It's not an exact science. Okay? Let's keep that up front. Scientists believe that our Earth has been completely ice covered at certain times in its history, the entire planet, as well as completely ice free at different times in our past. Okay? So what are some of the causes that cause these changes to occur in our climate that then influence our local weather? So, ice ages are more common on our planet than warm periods. We spend about 80% of the time with some ice on our planet. Who knew that we are currently in an ice age? Okay, well-informed people. We're in what's called the Quaternary Ice Age that began approximately 2.5 million years ago. We are still in that ice age. Ice ages tend to last many millions of years. Okay, so we're kind of in the early period of this ice age that we're in right now. We're currently in what's called an interglacial period of the Quaternary Ice Age that began about 12,000 years ago. That was the last kind of glacial period that we had when the ice sheets crept much farther towards the equator from the poles. And the Earth has been warming pretty much since that period, about 12,000 years ago. There have been 4 previous ice ages on Earth, 2 of which believed to cause that snowball Earth, if you will. So here is kind of an extrapolation of our period from present time to 542 million years ago at the top. So these are our temperature periods. You'll notice here, we're in this kind of ice age periods. Previously, 100 million years ago, it was pretty warm here, and there's been other pretty warm periods on our planet, much warmer than we're in currently today. Okay, just as a kind of reference. We've been in much colder periods as well. Here's the various ice ages down at the bottom. And you notice most of them lasted anywhere from 50 million years to sometimes 100 million years or more than 100 million years. So we're 2.5 million years in. The odds are this ice age is going to last for a long time. Okay? A lot more years of that we got to go through. So here's some other temperature data from the Vostok, which is in Antarctica. So pretty deep ice, about 8,000 to 10,000 feet of ice that they look through. And here we look at present time over on the left and 450,000 years ago. You'll notice it's a cyclical period. These warm periods that we have are pretty cyclical, about every 100,000 years. So we get warm, it gets cold again, warm, cold. Over on the left, where we are currently, is kind of another one of those warm periods. That's why we're in this interglacial period. Now, in the past, you notice when it gets really warm, what happens? It drops off pretty darn quick afterwards. So we're over here, but it's kind of hanging out here. So there's some speculation about this. So the last 100 and some odd years, goes back to 1880, these are annual mean planetary Earth surface temperatures. Northern hemisphere is in red, southern hemisphere is in blue. There's the actual data and the running means. So it actually cooled from 1880 down into the early 1900s. You notice that our planet was cool. And then it started warming. We went through a little cool period here in the kind of 1970s when some scientists were saying, hey, we're going into another ice glacial period. And then all of a sudden, it's been since 1970-ish, 1980, pretty constant warming. Notice that the northern hemisphere is warming more than the southern hemisphere.
More alignment.
So what is the average temperature differential between the low and the high?
Yeah,
50
notice
degrees, 1
here
degree?
we're at 0 degrees Celsius. These are tenths of a degree Celsius.
Tenths.
Tenths of a degree. Now, on a global period,
Tenths. I just didn't understand.
yeah, tenths of a degree. On a global period, if the temperature raises 1 degree C on a global basis, that's actually a lot of energy. Okay, that represents a large amount of energy that's available for things like weather to occur. But keep in mind, the sensors, there's a lot of debate on the weather sensors themselves. What is the degree of error in weather sensors? How does that play into that? So, let's see if this works. I don't think I have to log into anything here. So when I was at the European Center for Medium Range Weather Forecast, they had a video when I was in the center there over in Reading, England. And apparently we have to watch a small commercial. Unfortunate part of our internet. Okay, here we go. So this is a loop. Look at the year down at the bottom. We're in the early 1900s. This is the average temperature relative to the average. So these are the either above average or below average. Darker blues are in below average. The warm colors, yellow, reds, are warmer. So you notice since 1980, there's been a fairly significant change based upon the average of where the warming has occurred. So we can stop this now. So I found that interesting.
And Mike, is that relative to that last 30-year period then?
What's that?
Is that model?
No, it's relative to the
previous-
entire period.
Okay.
Yeah.
Why on averages do you only use a 30-year period? It seems to me that if you use the period of recorded history for that area, that you may be nominal.
Greg, you got me inside into that because I don't.
Not so much.
For whatever reason, it's what the NOAA National Weather Service has chosen to be their average period. I don't know why it was chosen, to be very honest. It's simply the way it was chosen and the way it's used. That video you saw was the entire average of the entire period, so it's relative to that.
Must have been a political decision.
So what causes some of these? When we saw that 100,000-year cycle with the spikes and the drops, what could potentially cause some of those changes? So we're gonna look at potentially what some of those changes can be caused by. One thing that a lot of scientists look into, and I'm kind of a big fan of these, are called Milankovitch cycles. So there's a Serbian scientist, last name of Milankovitch, who had a theory. It's still a theory, mind you. A lot of people have said, yeah, we're on board with this theory, but theories are theories. That there are different ways in which the planet changes its orientation that cause some of these climatic changes. The first one is what we call eccentricity. That's the change in orbit that the Earth has around the sun. Everyone, when I was young, I was taught it was a completely circular orbit. Well, no, it's not quite that way. We know that it can become more elliptical at certain periods versus circular. Obliquity. I was also taught when I was in school in 8th grade science, hey, the tilt of the Earth is 23.5 degrees. Well, this theory says no, that the tilt of the Earth actually changes. It varies. And then the last one is precession. In addition to the Earth tilting more or less, there's a wobble in that tilt. And those three things can work in conjunction to change the climate that we realize here on the planet. the theory kind of results in 100,000-year cycles, which from that data, we see that that's why a lot of people are kind of on board with this theory, is that the data kind of supports that 100,000-year cycle of these changes. So here's kind of the basis of it, is that our orbit around the sun changes, the tilt of the Earth and this wobble change with time. So eccentricity. So if we have perfectly circular, we have a 0 eccentricity factor. Okay? So the Earth varies from this 0.005, very, very circular, to more elliptical. Okay? Current value is 0.017. So we're a little more elliptical than the low period. The mean value is this 0.019. Periods move in these 100,000-year cycles. So when eccentricity is high, the Earth receives less solar radiation in a given year because it's farther away from the Earth. And as you get more elliptical, you're outside, you're not as close to the Earth, so we tend to have, this tends to be associated when you're high eccentricity, tend to be more associated with these glacial periods, cooling of the planet. Okay? Obliquity, so tilt of the Earth. Now, instead of 23.5, we've discovered that no, the Earth tilts really between 22 degrees and about 24.5 degrees. A couple of degrees makes quite a big difference in how much solar radiation you're actually getting.
Run my numbers.
Current value is about 23.4. That's what we kind of learned in science class. So high obliquity, when the Earth is tilted more, corresponds with these warmer periods because the portion that's closer to the sun gets a lot more solar radiation in a given year. As we go more of that less tilt, we're farther away. We don't get as much solar radiation. So those are more with the glacial periods. Okay, the last maximum was during pretty close to when our last kind of glacial period was, and the next minimum is 11,800 years. Quite a while from now.
So you're saying the obliquity is a decreasing parameter?
Yes. Yes. So the current theory would be the Earth to be in a cooling trend because of this one particular pattern. And then we have this wobble. So the wobble is on about a 26,000 year cycle, and it's due to gravitational forces of the sun and moon that play on the Earth. So what we call perihelion is when the axis is pointed toward the sun. Aphelion is when the axis is pointed away from the sun, the wobble portion of that. So the hemisphere with this perihelion during summer and aphelion during winter has more extreme seasons. Okay? And currently the southern hemisphere is in this phase. So that may be one reason why the southern hemisphere is not warming as much as the northern hemisphere right now. Okay, so what are other factors that influence climate? So volcanic eruptions. We know when there are major volcanic eruptions, there's a lot of volcanic ash that makes its way all the way into the stratosphere. When it gets into the stratosphere, it's a very stable layer in the atmosphere, and it stays there for a long time. And it can spread over the entire globe for some areas. And so that tends to cool the Earth down because not as much solar radiation is making it all the way to the Earth. We know that meteor impacts can have a large impact on weather. If they put up a lot of dust or particles into the atmosphere, that would also be a cooling effect on the planet. Solar cycles. We know there's 11-year, these solar sunspot cycles, but we don't have a clear indication of how they play into our weather and our climate patterns. We just don't have a lot of causal links right now, correlations to know that. And then we have the last one, which is the political. Greenhouse gases. So greenhouse gases naturally exist in our atmosphere. Okay? It's made up of CO2, carbon dioxide, methane, ozone, nitrous oxide, and water vapor is another greenhouse gas. And the theory goes, the more greenhouse gases you have in the troposphere, radiation tends to pass through those pretty easily. So it makes it all the way to the Earth. When the Earth re-radiates that solar radiation back out to space, these gases absorb that radiation, that heat, and they retain it. So that's why when you have more greenhouse gases in the atmosphere, the Earth tends to get warmer because it retains the heat. It's not allowing it to escape back into space. Okay?
Can I give you another one?
Sure.
undersea volcanic action changes water temperature in areas, which change this El Nino thing,
Yep.
and that's not even talked about under volcanic eruptions. What happens undersea? We don't really know, but we do know that increased volcanic eruption can change sea temperatures.
Absolutely, and I'll get to some of the oceanic stuff here in a bit, and that plays a huge factor in our weather. There's no doubt about that. These are more on the climate side, the longer term kind of averages. But you're right, there's a lot of things, a lot of phenomena that we don't know how they play into this equation.
Now, if the dinosaurs became extinct, there's less methane.
Yes, yes indeed, that's probably very true. So, our current climate, from my perspective, is pretty darn comfortable for human activity. If you think about a planet that had 3,000-foot ice sheets over the entire planet, it'd be hard for human activity to exist. Even in the last glacial period, we had ice sheets 3,000 feet thick that extended down into the Great Lakes and the northern tier of the United States. Think of how do you grow food, how do you do a lot of things when you have 3,000 feet of ice on top of you. It would make life very difficult, very different than it is today. But also a warmer planet implies more dramatic weather patterns. And that's because if you have more heat in the atmosphere, in the oceans, you have more energy to work with. Systems can become more dynamic and more intense the more energy you provide to them. So as the oceans got warmer in the Atlantic this year, you notice hurricanes developed very rapidly and intensely. So we had 3 Cat 4 storms that actually made landfall in the U.S., pretty unprecedented. It's largely driven by the temperature of the ocean. The Gulf of Mexico and the Atlantic were very, very warm in that period this year, and allowed those storms to intensify to a great deal. So we tend to have more extreme floods, more extreme droughts. Sea level rises as some of the ice is melting in the polar regions. And as population increases, those impacts become more dramatic, both on the flooding, the sea level rises, all that kind of stuff. And this is simply what caused the warming. We're not going to talk about too much. But our planet is warmer than it was 100 and some odd years ago. So from my perspective as a meteorologist, we're going to see more dramatic weather as that warming continues. Yes?
Mike, I remember back doing old fart myself. I remember that in the early 1970s, he told us that by the year 2000, we would have freezing temperatures in the summer. Where did we get that?
So when we look at that graph that I first showed, we noticed there was a little cooling period from about 1950 to about 1970 or so. And that's when scientists started kind of latching on to the Milankovitch theory. They started looking at that and going, wow, our temperatures are declining, we're in this cycle. They thought temperatures could continue to decline, that we're headed for another glacial period. That was some of the thinking at that time, not all the scientific thinking. That was actually a small percentage when you look back at the papers that came out during that time, but it got caught onto by the media. And so, there was that small portion of scientists who thought, yeah, maybe we're headed into the next glacial period. Turned out not at all to be true, of course. So, if we use Milankovitch theory and past records, the Earth will likely enter another glacial period sometime in the next 5 to 50,000 years. We simply don't know when that's going to be, and we don't really know what the triggers are. We know it happens fairly quickly, but we don't know the exact triggers of how that occurs. None of us are going to be there, is my point here. So enjoy the time we have on this planet. It's pretty darn comfortable. But future generations, if our species manages to get along and survive this long, are going to have to go through some pretty serious climatic changes and how they're going to adapt and survive on the planet. As I said, past ice ages last a long time. We're going to be in ours for quite a while. We don't know, the trigger events of what causes these or whether they're gradual and they just look more extreme on the graph because the years are kind of compressed. So we don't know if the current warming trend that we're in is offsetting this eventual drop in temperature or what it's going to do. There's a lot of uncertainty.
So you say we've only been in our current ice age for 2.5 million years?
Yes.
Are we in one now?
Yes. Yeah, it started 2.5 million years ago. Yep.
But we're warming up.
Yes, we're in an interglacial period. We're in a warm portion of the ice age, and we don't know how much longer it's going to last. Is the point? You have a question?
Yeah, if I could ask you to take off the middle of the bottom bullet and just use the words, we also do not know if the current warming trend will continue to offset the expected cooling trend.
Right. We don't.
Because that is, what's in the middle of that isn't true.
Well, there's a debate. I'm going to try not to stay away from that. There, in the scientific community, which Greg and I are part of, we know the theory of you increase greenhouse gases, temperature goes up. There's a very strong correlation. How much humans have contributed to that is a topic of debate, and whether it's the primal cause. A lot of scientists believe it is, some other people don't. Everybody can have their own belief about what's going on. My point about this whole thing is not so much what caused it, simply that it's occurring. The warming is occurring. I think
Well, thank you,
hopefully
you're actually making my point. It's not so much about what caused it, but you're putting the cause on that chart.
well,
Remove the middle of the last paragraph.
like I said, we'll stay out of the political side of this.
Well,
We'll all agree that
I
it's
appreciate
warming.
that, but you walked into it by adding that on the
Well,
chart.
that's my belief, so I get to put it on my slides. If you talk about it with friends, you can frame it however you want. That's my personal belief. The point is, I'll get to this in a second. The point is, we know that the planet's warming. There's going to be some impact. So as a society, how do we handle that? And that's the part I let policymakers, politicians, the one determining policy and how we go about this. Whether we do absolutely nothing and just let the earth be as it is, or if any changes we make, what do we do? How do you prepare for potential sea level rises, potential more flood and drought, more extended fire seasons, etc. So as a society, to me, that's a question to the broad scope of whether you do nothing and just let climate be what it is, weather be what it is, or do we take some preventative measures to try to minimize the impacts to the society? It's a question. I'm not stating one way or the other. Yes, sir.
Yes, you are.
I'm really not. Yes, sir.
Would it be correct to say that dramatic weather has been decreasing over the last decade and not increasing? I mean, the
So,
hurricanes that
yep.
have been striking the North American continent has gone down by about 40%.
Yeah, so I've seen papers kind of going both ways. I've seen some papers that have said the impacts, the cost to society has been going up in the last, let's say, 30 years since 1980. I've seen some that said it's the same, and I've seen some that said they're decreasing. There's not a consensus on which way that's actually going. Is the best I can tell you.
At the risk of being very obtuse, here's a hypothesis if you could test. Take a look at Mars atmosphere, 95% CO2. Take a look at the relative density of the atmosphere, which is what about 100 times less the Earth. Look at temperature gradients there and compare them to the Earth, which has obviously a denser atmosphere with a much lower carbon dioxide percentage, and see if there's some relationship there that suggests that CO2 really is contributing at an equal rate or disproportionate rate to warming.
Yeah.
Let's get on that.
I'll leave that to people with a lot more knowledge than myself.
Yeah, I mean,
to test that.
this is a presentation about pilots flying in mountains. This is not a presentation about what's causing global warming.
And I'm not trying to cause what's happening. I'm just saying, here's the impacts. We're going to get to here some influences that may impact you on a daily basis. So the long term is climate, which we've talked about, what causes some of the changes to our planetary climate. These are now influences that act on a more smaller scale time-wise in a season, for example. So we have this something called El Nino Southern Oscillation. That refers to this warm body of water, warmer than average water in the Pacific Basin. It's either on the east side of the Pacific Basin towards North America and South America. That's when we call it an El Nino, or a warm phase of ENSO. Or the warm water sits on the western side over towards Asia and Indonesia. We call that La Nina because then cooler water is on the eastern side. So the warm phase, again, it's based on 0.5 degrees Celsius of what we call sea surface temperature anomalies, either warmer or cooler than the average period since 1950 is when we started kind of making these measurements. So the warm phase is El Nino. We saw this a couple years ago out here in Colorado. We had a very strong El Nino event, and there was a direct impact to the weather here in Colorado. La Nina, we're currently in a La Nina phase right now, and it's again, there is a direct impact to the weather here in Colorado. There's been this upper level ridge that has sat along the west coast since basically mid to late November that has impacted our weather here in Colorado. We've had very little precipitation, and we've had much warmer than average November. December, depending on which way this ridge moves, if it moves out farther into the Pacific Ocean, so it's farther to our west, we tend to get colder air coming down from Western Canada. As that ridge moves a little bit west into the Great Basin, it tends to be much warmer here in Colorado and drier. So we'll look at El Nino. This is the sea surface temperature, the actual sea surface temperature, and these are the anomalies. So notice during an El Nino, this warmer than average water is on the eastern side of the Pacific. La Nina, we have much cooler water in the eastern Pacific, warmer water is back over the western. When we have these neutral conditions, it's neither warmer or colder than average, it's about average. Water's about average. So there's really three phases to this cycle that we deal with from a weather standpoint. 1997-98, we had a very strong El Nino event. You can see this very warm water here off the coast of South America. The following year, it was followed by a very strong La Nina event, very cool water in the eastern Pacific. And we had very different weather in North America 1 year apart based on this pattern. So the Oceanic Nino Index is this number in degrees Celsius of which way from average that temperature is going in the eastern Pacific. So the positive ONI is the El Nino event. When we have an El Nino event, we tend to have a stronger zonal flow from the Pacific all the way across North America. Zonal means strong west to east flow, upper level flow. Okay? Subtropical jet stream tends to provide additional moisture up into the southern tier of the United States, and we tend to have above average precip along the southern third of the U.S. and below average in the northern two-thirds. The temperatures tend to be cooler along the southern U.S., warmer in the northern U.S. For Colorado, we tend to have some of our snowiest seasons during El Nino events. Eastern Colorado specifically tends to get much more snow than average during El Nino events. This is what a El Nino kind of looks like. This is from Mike Baker at the National Weather Service. Jet stream sags much farther south out in the Pacific. We tend to have higher pressure or a ridge up in the Pacific Northwest, so they tend to be real dry. Much wetter across from all the way from kind of central Southern California, Arizona, New Mexico. And as these systems run along the jet stream, this is why we tend to get these upslope storms here in eastern Colorado, because the lows tend to be to our south, giving us those good upslope storms. And you notice a lot more precip southern tier, warmer and drier northern tier states. And this is what the precipitation anomaly, wetter along the southern tier states. And temperature-wise, again, cooler in the southern, warmer in the northern tier. So La Nina, it's the exact opposite. Colder water in the eastern Pacific. We tend to have higher amplitude, which means big ridges and troughs in the atmosphere when we have a La Nina season. And we've seen that this year. We have this massive upper level ridge that's been sitting along the west coast. So air goes way up into Alaska and western Canada and then comes down. And so the position of that ridge determines where the cold and warm air is. The eastern U.S. has been very cold lately because all that cold air is coming down over the eastern U.S. So we tend to have above normal precip, below normal temps in the Pacific Northwest Great Lakes, the northern tier, and we tend to have drier conditions southern tier. So it's really just the exact opposite of El Nino. For Colorado, we can get above average snow in the mountains. If we have that northwest flow that's coming down, it has enough moisture, the mountains can actually get a decent amount of snow. But it tends to be drier across eastern Colorado, and we tend to get more downslope winds, which create warmer conditions east of the mountains. Yes. Yes, it snowed in Houston, it snowed almost in New Orleans. For the season, it probably will be, but there will be periods when you have these high amplitude patterns, we can get very cold air that comes very far south in the U.S. So it really depends on the pattern as to what ends up being the actual temperature and precipitation anomalies. But no one can really predict ahead of the season where that ridge or how big the ridge is going to be. We just know that the ridges, strong ridges and troughs are more prevalent during La Nina seasons. So right now it tends to be right along the west coast, which means, yeah, colder air is coming into the deep south. But it looks like that may change eventually, but for right now, the past 3 weeks, that's the way it's been. So this is kind of what a La Nina pattern looks like. Right now, instead of this, we have more of this. Big ridge and air coming down. But that's why you tend to get colder air across the northern tier states. We tend to have more what we call Arctic air outbreaks during these La Nina seasons because of the high amplitude season. So Colorado can get these really cold Arctic air intrusions during La Nina seasons, but over the entire season, we tend to be warmer because of this northwest flow, because we get the drying and the warming conditions over eastern Colorado. Even though you can have a week or two periods where it's very, very cold when you have that Arctic air coming in. So typically we tend to have drier air, wetter Pacific Northwest, Great Lakes, also during La Nina seasons, as we've seen last week and this week, a lot more lake effect snow as well. For those who have lived in that part of the country, that tends to be a pretty consistent phenomenon during La Nina seasons, is that lake effect snow. And temperatures, we just tend to be colder northern tier. So, like a lot of things in weather, everything's very cyclical. So if we look, this goes back to, I believe, 1950 on the left-hand side, present time over here. Here's the average line. You notice there's been a lot of El Niños, a lot of La Niñas. It's a very cyclical pattern. Some decades tend to have more of one than the other, and we'll look at that as a Pacific decadal oscillation. But you notice here, 2015-16 had this really strong El Niño. And again, we had higher than average snowfall in eastern Colorado. In the last 2 years, we've been down in this La Nina pattern, which has been drier than average for most parts of eastern Colorado, this year included. So if we look at these ENSO patterns, 1950 through 2016, that's about 67 years, the Denver average snowfall right now is about 57.5 inches. When we have these warm episodes, 20 El Nino episodes, 15 of which have been moderate to strong, notice the average snowfall goes up. 63.8, and it goes up to 68 during these stronger, moderate to strong El Nino events. La Ninas, we've had 9 of these. Average snowfall is a little bit lower than average. And it goes, when we have a strong La Nina, it goes way down to 51 inches. And we've also had 24 neutral episodes. And there, the average snowfall is pretty close to average. So currently, in our current configuration here, we are in what's called a weak La Nina. The ONI is minus 0.8. So it's in that weak La Nina. Notice here, cold water out in the equatorial Pacific, eastern Pacific, warmer water as we go into the western Pacific. Yes?
Mike, when we talk about snowfall, is there anything that standardizes the moisture content there, or is it just the height of, like 12 inches of snowfall could either be 12 inches of light fluffy stuff or 12 inches of tremendously dense stuff?
Yeah, the colder the temperature, the larger the ratio to snowfall to liquid precipitation. So if the temperatures are really cold, we tend to have greater snowfall. It tends to be, in Colorado, what we'll call average is 10 to 12 inches of snow per 1 inch of water. Very cold temperatures, it goes up to anywhere from 12 to 20 to 1. Okay. Warm temperatures, like if you go into California, into the Sierras and the Cascades, it tends to be down to 6-to-1 or 8-to-1 for snowfall to liquid ratio. So warmer temps, lower ratio, colder temps, higher ratio. So the way the models are predicting our season to go is that we're going to continue to be in this kind of weak to moderate La Nina phase all the way into basically springtime. And then it's going to start going back to neutral. Some models are saying potential warming, but most of them are in this kind of neutral category as we go into the summer period. So for this winter, it's pretty much guaranteed we're going to stay in this La Nina phase through springtime. So what does that mean for us? So this is the Climate Prediction Center outlook. When we look at a 3-month outlook here from December through January and February, temperature-wise, the western U.S. looks to be warmer than normal, colder than normal, Pacific Northwest, kind of northern plains and Great Lakes area. Pretty typical of a La Nina season. Precip-wise, same thing. Wetter across the northern tier, drier across the southern tier. So pretty typical La Nina type season is in store. So there's other oscillations that people tend to look at. There's this, what's called the Arctic oscillation. It's the sea level pressure difference between the Arctic region and the mid-latitudes. Positive AO, representative of a strong zonal flow, just like an El Nino kind of situation. Negative is the other way, higher amplitude. North Atlantic oscillation, very similar to the Arctic oscillation, measures sea level pressure difference between the Icelandic low and the Azores high. This is that Pacific decadal, so it takes that ENSO over a decade and says which pattern is stronger or more prevalent than the other. So you notice certain decades have more La Ninas or more El Ninos. And it oscillates. And then there's this thing called the Madden-Julian oscillation. So it's more of a 30 to 60 day pattern. And it really is this kind of wave that moves around the equatorial regions all the way around the globe. And so when the positive phase of this wave is over towards North America, we tend to have enhanced precipitation here in Colorado. When we're in the negative phase, which we've been in the last month or so, we tend to have drier weather here in Colorado. And I'll show you kind of what that looks like. This positive phase of the Madden-Julian oscillation kind of moves along the equatorial region, and as it gets closer to North America, that tends to enhance our precipitation here in Colorado. Currently, this is a positive phase, so this was back last year, February of 2017, when we're having a fair amount of snow here in Colorado. And then we've had this big negative phase associated with that big upper level ridge that's been over the west coast. And you notice it's been much drier over Colorado during this phase. There is some hope that this area here is starting to be a positive phase in the MJO, and it may move towards North America potentially like in January. We may see a little bit of change in our weather pattern, but yet to be determined. So for Colorado, again, the La Nina looks like it's going to stick around. It still favors that wet and cold pattern across the northern tier, dry and warmer across southern. As we've seen in Colorado, it's been pretty dry. The mountains could still get some snowfall if that upper level ridge kind of either breaks down or moves a little bit farther to the west. And we still could get some powerful winter storms. Even though this pattern may be prevalent, it can break down for a week at a time or 2 weeks, and we get more precipitation. So it's not something that usually hangs around all winter long.
What do you think with this?
That was an odd one because everybody kind of thought the El Nino the prior year would be when California would get a bunch of precip, and they really didn't. And it was kind of surprising. Last year was kind of a weak La Nina, and they got it's called this atmospheric river event, where you have this stream of moisture that comes from kind of off Hawaii over to California. Every year is different. It's about all I can say. We still don't know exactly what's going to happen every year. We get signals from the ocean that kind of tell what we think is going to happen in the atmosphere, but it doesn't always work out that way. Yeah, really doesn't. Okay, so we're at our next break.
Cool.
Yeah, sometimes lenticulars can be pretty cool. When you get what's called an isolated peak event, you can get lenticulars that form around this isolated peak. So you can get some pretty fascinating pictures. I believe it's not Fuji in Japan. Yeah, so yeah, pretty cool stuff. So we have another opportunity for you to win both a weather book and a membership to the Colorado Pilot Association. Of these 4 cities, which has the highest annual average snowfall? Again, 1 out of 4 chance.
Wow.
And put your name in, because we're going to draw for the other one as well. So again, put them up on the laptop there, and we'll take another 10 or 15 minute break. When we come back, Greg's going to talk about his updated weather app.